Okay, so thank you for coming. So tonight I'm going to talk about galaxies which are forming more stars than any other galaxies in the history of cosmic time, and yet which are completely or nearly invisible to even the world's most powerful telescopes. So I'm going to talk about why that is, and the lengths that we have to go to find these galaxies. And finally, I'll end by talking about what we actually discover when we do see these galaxies. Is this okay? I'm getting a lot of feedback up here. Okay, great, thanks. So first I'm going to zoom out and try to put these galaxies in the larger cosmological context. So around 13.7 billion years ago, the universe began with a Big Bang, after which it was filled with radiation and ionized matter. As the universe expanded, it cooled to the point where this matter could begin to form some of the first stars and galaxies. And we think this happened around 400 million years after the Big Bang. The galaxy growth accelerated, ultimately peaking around 2 to 3 billion years after the Big Bang in what is known as the era of galaxy assembly. And the galaxies have continued to grow and evolve since then, all the way to the present time, including forming our own sun and Earth about 9 billion years after the Big Bang. So clearly, in order to understand the universe that we see around us today, we'd like to have a complete picture of this entire galaxy formation process. It may surprise you then to learn that the observations that really form the basis for our understanding of galaxy formation and evolution are only telling part of the process, part of the story. So in particular, the optical telescopes, which have really pioneered our understanding of galaxy assembly, are only sensitive to the starlight that's not blocked by cosmic dust. And it turns out that most of the star formation in the universe occurred behind interstellar dust grains. So this means, although optical telescopes, like the very famous Hubble Space Telescope that you see here, may be showing us a picture of something like this, we think that the actual picture is something more like this. So does this problem affect all galaxies equally? That's a good question, right? And the answer is no. It seems that galaxies in this era of galaxy assembly are most affected by this problem. And in particular, the galaxies that are forming the most amount of stars are suffering the most. So these are these monster galaxies that I was referencing in the title of the talk. So what do I mean by monster galaxy? So to try to put these galaxies into context, our Milky Way forms approximately 1 sun-like star per year. So I see a lot of astronomers in the audience. So does anybody who's not an astronomer want to guess how many stars per year these galaxies form? 200? Other guesses? 1 million. Okay, that was overshooting. Yeah. So they form a lot of stars. So I actually ran out of room on the slide, but they can form up to like 1,000 sun-like stars per year, or even more. So this is 3 orders of magnitude more star formation than we see in our own Milky Way. And this means that even though these galaxies are actually quite rare, they make up a large fraction, they literally make a large fraction of the stars that are formed during this peak era of galaxy assembly. So this makes them really important to identify and try to understand. So here is an optical image of a region of the sky where we think one of these monster galaxies lives. This is an incredibly deep image taken with the Hubble Space Telescope, which is one of the most powerful telescopes in the world. Does anybody want to guess which galaxy is this monster galaxy? A black spot? A gap. In the gap, yeah. Okay, well, the point is that it's none of these very bright things that you might see by eye. So actually, it's this tiny little speck right here. When we zoom in, this is what we see after integrating for hours and hours and hours on the Hubble Space Telescope, one of the most powerful optical telescopes. So we're only detecting a tiny fraction of the light. And how do I know that? Well, because we know that the galaxy actually looks like this. So how do we know that? Well, that's the point of the whole rest of the talk, so I'll come back to it. But unfortunately, what it means for us is that, for example, if we are looking in the optical with Hubble, all we're seeing is this. So this is obviously a problem. It makes it really hard to understand what's happening in these galaxies if this is what we have to go off of. And in particular, we still don't understand how these galaxies are forming so many stars so quickly. So there have been a wide range of theories. One of the most prominent theories is that these galaxies are formed by two massive galaxies that are smashing together. But obviously, it's hard to test this theory and other theories if this is all that we have to go off of. So how do we actually see these galaxies? The answer is that we have to use a different part of the electromagnetic spectrum to effectively see through the dust. So what I mean by that is that the starlight that is emitted in the short wavelengths that are detectable with optical telescopes is absorbed by dust, and that's why these galaxies are effectively or completely invisible. However, the dust then re-radiates this starlight at longer wavelengths. So by looking directly at the longer wavelengths, we can effectively see this missing starlight. And we're very lucky that we have a brand new fancy telescope which is able to see at these long wavelengths. And that telescope is the Atacama Large Millimeter Array, or ALMA. So ALMA is a powerful new long wavelength telescope in the Atacama Desert in the north of Chile. It was an international partnership between Chile, Europe, North America, and East Asia. It cost 1.4 billion euros to build, which makes it the most expensive ground-based telescope ever built. And this is a picture of me at the Alma site in 2015 during our commissioning campaign, where we were trying to incorporate more dishes into the Alma array. An interesting thing to note about Alma is that it's at an elevation of 5,000 meters, so over 16,000 feet if there's any other Americans in the audience. And it's also at one of the driest sites on Earth. And this is really important for these long wavelength observations because it basically minimizes the amount of water vapor that is in the atmosphere that would then distort the astronomical images. However, such a high elevation, 5,000 meters, is not particularly hospitable to life. So if you look in this image, you might notice there are no plants anywhere to be seen, for example. The elevation is also really hard on humans. So this elevation is similar to the elevation of the base camp to summit Mount Everest. So at elevations like this, humans can develop mild or even severe altitude sickness if you're not properly acclimatized. So this makes this a really extreme environment to work in. It means that if you want to work here, you have to take a high altitude medical exam. And while you're at the site, you have to monitor the amount of oxygen in your blood with a little thing that clips on your finger. And if you find your oxygen is low, like you're feeling particularly giddy, like I've felt before, then you may have to use the emergency oxygen that you have to carry with you at all times. So what makes Alma special besides its particularly high elevation? It's not the first millimeter telescope to ever be built. But the thing that's tricky with these long wavelength telescopes is that the angular resolution you can achieve with your astronomical observation is proportional to the wavelength over the diameter of the telescope. So what this means is that if you take a short wavelength observation of it using a telescope of a particular diameter, and say, just for example purposes, that you get an image like this, then if you were to use a telescope of exactly the same diameter, but now you were to observe at longer wavelengths, then your image would now look like this. So the angular resolution would be degraded. So you can also see what the solution to this is by looking at this equation here, and that is you also need to increase the diameter of your telescope. You need to increase the denominator here. So how much would we need to increase the diameter of the telescope to achieve similar resolution as to what we can get at short wavelengths? So for example, if we wanted to match the angular resolution that we could get with the Hubble Space Telescope, but instead at the wavelengths that Alma observes in, we would need a telescope with a diameter not just the size of one football field, but 24 football fields in diameter. So you can imagine it's quite difficult to build a single telescope of this diameter, right? So the way Alma does this is by building lots of smaller dishes and then using them all together as one giant telescope. Unfortunately, it means it's hard to get a good image of the telescope because it's so spread out. So here you can see some of the dishes in the array, but I wasn't even able to capture all of the 66 dishes in the array. Some of them are out of the field of view. But the 66 dishes also give Alma an incredible collecting area, which means it's a lot more sensitive than previous telescopes at similar wavelengths. Another special thing about Alma is that it can control its angular resolution by actually moving the telescopes closer together, the individual dishes closer together or further apart. And it does this by picking up each of the 100-ton dishes on one of two specially designed antenna transporters, which themselves are 130 tons and have 28 wheels each. This is such a delicate process that when the drivers get close to the antennas for the last steps of the process, they actually control this giant machine using a remote control, which I think probably makes this one of the largest remote control cars in the world. So once the telescopes are loaded onto the antenna transporter, you can then move them to other locations. So here you see a telescope that's in the process of being moved. And I'd like to on the door here. So right at the end there, you might have seen the door open as the transporter slowed down, and that's because the driver pulled over and offered me a ride. So the incredible increase in angular resolution and sensitivity that Alma gives us means that whereas before, if all we could say was that there's one of these extreme galaxies somewhere in this field of view, now we can say that it's precisely here at a distance of about 12 billion light years away and forming about 650 stars per year. And here's another example where we knew there was one of these extreme galaxies somewhere in the field, but we didn't know where until Alma came along. And now we can say that it's precisely here at a distance of about 12.5 billion light years and about 1,500 stars per year. So Alma's incredible angular resolution means that we can not only find these galaxies, but we can see a level of detail in the galaxies that's far greater than we were ever able to see before. And what we find when we look closely at the galaxies is that the contrast is a little off here, but basically they look very similar to disk galaxies that we see in the local universe. So here on the left is one of these extreme galaxies seen very close to the beginning of the universe, and on the right is a disk galaxy that's just right next door, a normal disk galaxy. We also see some evidence for spiral arms in these galaxies, which is another thing that's very common in local galaxies. But here we're seeing it in a galaxy that's about 12 billion light years away compared to a galaxy that's, again, just next door. One final example, which is again highlighting the similarities that we see between these galaxies and the nearby galaxies. And this is incredibly surprising because these galaxies are forming more stars than any other galaxies in the entire history of cosmic time. Based on our theories, we thought that they would be two galaxies smashing together, and that's not at all what we found. Instead, we found that they look surprisingly normal. So, thank you.